All right, everyone. Greetings. In this set of slides, we're going to be talking about some social vulnerability measures that will help us analyze networks of communities. So just a little bit of a recap, what we've discussed so far in the course. We've talked about a few graph theoretical measures, a few network science measures for describing characteristics of networks. Talked a little bit about network optimization from a basic perspective, and we'll talk a little bit more about that in this set of slides. Then you've seen some presentations that might deal with decision support tools for visualizing networks, in particular infrastructure networks, and some predictive analytics models for describing network behavior, in particular service networks. So you've had a good idea so far about physical infrastructure networks and service networks. And so in this set of slides, we're going to be kicking off the community networks topic. Thus far, we've talked about really the physical networks, physical infrastructure networks, and service networks. And we've hinted at bigger reasons about why it's important to study these physical networks, because they don't exist on their own. They didn't just sprout up out of the ground just because. They exist because we need them to. They exist because we, as people, as societies, use them and need them for productivity, for health, for just our flourishing, right? So they exist for reasons beyond just existing on their own. And so whenever they're disrupted, there are impacts beyond just, an electric pole being down. There are broader impacts to those physical infrastructure networks. There are reasons why service networks are engaged, and it's because we need them to be. So recall this idea of cyber-physical social networks. You've seen this picture before, but let's just talk about it again. We've got these infrastructure networks, these physical lifeline infrastructures like transportation networks and land waterways and rail and that sort of thing. We've got water networks in the form of fresh water and wastewater, and we've got electric power. Those are some examples. There are other infrastructure networks, of course, but these are some popular ones and ones that we've talked about over and over again in this brief course. And then we've got those community networks that reside on top. The reason for those physical infrastructures to be in the first place is because we need them to, and whenever they're disrupted, then we're disrupted. And then service networks are engaged after a disruption to repair us in the form of humanitarian relief and emergency response, and to repair the physical infrastructure in the form of restoration crews. And so this gives us a picture of the enterprise of entities that can be disrupted, what becomes engaged, and so on after some sort of disruptive event like a natural hazard or other kind of disaster. And so what we want to talk about in this set of slides and might set up future lectures would be, what are some indicators of community resilience? What might make a community resilient to disruptions in infrastructure networks, and just more broadly, disruptive events, natural hazards, and so on. And so here are some physical characteristics that might seem reasonable to be indicators of community resilience. For example, evacuation potential. So what is the arterial highway situation in a particular area? How easy is it for people to evacuate if they need to? Housing age. Newer houses might be built in a different way, might be up to a different kind of standard than older houses, for example, or apartment buildings. So the older ones may not be able to handle disruptive events like newer ones can. Some health-related characteristics. The numbers of physicians or medical capacity that exist for a particular area. That might be an indicator of an ability of a community to withstand some kind of disruption, especially if there are health effects of that disruption. The locations and capacities of shelters in particular communities, right? And these would be indicators of a geographical area, you know, in a county. How can we describe the shelter locations, distance to shelters, and the capacity of those shelters for a given community, a given location? Some characteristics of the population, and I'm going to be talking more about some socioeconomic characteristics in a bit. I just want to point out, and I'm going to say this probably multiple times, this is not my research. Okay, this is research that comes from other sources. These are statements that I haven't tested. I'm not a social scientist, and the purpose of this course is not to test some of these theories, but they might be usable nevertheless. And they are certainly put together by people who have studied this issue far more than I have from a social science perspective. So I'm going to have to rely on their research. Okay, so there's some characteristics of the population. For example, inequalities that may exist among races in a particular location, right? The wider that disparity, perhaps the less resilient that community might be. Inequality with respect to educational attainment. The existence of previous disaster experience. You might imagine that if more people have experience with a disaster in a particular location, they might be able to withstand and adapt to and recover from another disaster just because they've been there before. Percentages of population with healthcare coverage. Naturally, the healthier a population, the better able they might be to withstand some sort of disruptive event, and so on. And so we probably talked about this presidential directive before, and if we haven't, this really, a similar presidential directive before this, back in the early 2000s, really kickstarted this concept of resilience. And it was updated in 2013, and it's still relevant today. So this directive states that the critical infrastructure must be secure and able to withstand and rapidly recover from all hazards. Back in the 2000s, or in the decade of the 2000s, this would have been called an all hazards approach. The government was spending quite a lot of effort in understanding how to respond to not just a hazard, but try to build resilience to multiple hazards. And they refer to it as an all hazards approach. The resilient operation of critical infrastructure is essential to the nation's security, public health and safety, economic vitality, and way of life. And there was a particular document from the National Academies of Science that tied together this idea of physical infrastructure resilience, just broadly speaking, resilience to infrastructure damages, resilience to different kinds of disruptive events, and community impacts. And the quote here is, one way to reduce the impacts of disasters on the nation and its communities is to invest in enhancing resilience. And then more recently, the National Institute for Standards and Technology defined community resilience in particular as the ability of a community to prepare for anticipated hazards, adapt to changing conditions, and withstand and recover rapidly from those disruptions. Now, that's very similar to other definitions that we've seen of resilience in general. And so you might imagine, you know, this idea of resilience can be applied in a variety of ways. Processes and systems, physical infrastructure networks, operations, businesses, and people and communities and society, right? If you've got a way to understand how people respond to things, how a business responds to things, how a physical infrastructure network responds to things, then you have some notion of its resilience and its ability to withstand disruptions. So a resilient community would ideally be able to use the physical infrastructure to effectively communicate risk and coordinate recovery strategies, respond to and recover from disruptions, and ultimately adapt to change and learn from past disruptions. Okay, so the idea here is that a resilient community might have some intrinsic characteristics of the community itself that might make it resilient to disruptions, but it also needs that physical infrastructure networks, the set of physical infrastructure networks to be able to effectively communicate, for example, before, during, and after some kind of disruption. Needs some ability to have experienced and can learn from past disruptions and so on. And so you remember the old resilience figure that we talked about before. Let's talk about it briefly again. So we've got some performance measure, phi, that describes a process or system or a community or whatever it might be over time. Okay. And we see that it's operating at some baseline level until some disruptive event occurs. And then that performance degrades in some way. And we refer to that drop in performance as vulnerability, broadly speaking. And then after some amount of time, we start to see some improvement in that performance, some sort of recovery, which we refer to as recoverability, until we achieve some sort of desired stable recovered state, okay, which may or may not be the original recovered state. And so what we're going to talk about here is social vulnerability. And that's the term that's used in this particular community, this research community, not to be confused with our definition of vulnerability here. We refer to vulnerability as the drop in performance after a disruption. Here, social vulnerability refers to, I guess, the ease with which, well, we'll see a formal definition later, but the ease with which a community might be vulnerable to a disruption. And so we see this plot here from Cutter et al. In 2003. I'll mention that Susan Cutter is a social scientist at the University of South Carolina, considered an expert in the area of social vulnerability, and we're going to use her work extensively in this set of slides. And so this figure describes essentially social vulnerability and some elements that make up a study of social vulnerability. So there's some measure of risk, some measurable indicator of risk to a risk associated with a disruption. And there's some way to mitigate that risk, whatever that might be, the implementation of resources to reduce the likelihood of impact. And those two combine, so this inherent risk, this ability to mitigate that risk, those two things combine to describe the potential of a hazard to lead to some sort of disruption to a community. And that hazard potential results in essentially a, let's say, the context, the geographic context, the geographic location associated with the potential hazard. Okay, so what are some characteristics of the geography that might make it amenable to a disruption? Elevation, for example, proximity to where the hazard is located. If we're talking about proximity to a fault line, could be proximity to an ocean where sea level rise is occurring or where a hurricane might occur. Proximity to Tornado Alley here in Oklahoma, right? So there's There's some geographic context associated with that hazard. And then there's some social context associated with that hazard, right? What is the community that's being affected? What are its characteristics, okay? Experience with previous disasters, the built environment associated with where that community is residing, and so on, right? So there's potential for a hazard that's a function of risk and mitigation. It affects the area where that hazard might occur. It affects the people in some way where in that location, right? And those two are related to each other. The geographic context creates some physical vulnerability. The social context creates some social vulnerability. And the combination of those two produces what is referred to by Cutter as place vulnerability. It's essentially just the combination of the physical reality of where the disaster might occur, this disruptive event might occur, and the people that reside in that physical location. Okay, and then based on that combination, that could affect the risk, and it could affect how we choose to mitigate that risk. Okay, so that's a way to describe the vulnerability that extends from some kind of hazard risk. And so social vulnerability refers to the response of communities when they are confronted by external stresses such as natural, systems-based, or human-caused disruptions. Okay, so we could be talking about a natural disaster. We could be talking about an accident that occurs, or some malevolent act. Whatever it might be, social vulnerability refers to the response of communities to whatever that disruptive event might be. And so, if we're referring to a particular geographic location, the exposure of a disruption might be the same to every individual that exists in that geographic location. However, depending on the social vulnerability of the groups within that location, the impact, the consequences might be different. So exposure might be the same, risk might be the same, but consequences might be different depending on the characteristics of the community that resides in that location. So perhaps an extension of the definition of social vulnerability is this one: set of characteristics of a group or individual in terms of their capacity to anticipate, cope with, resist, and recover from the impact of a hazard. Okay? This would probably be, actually, this is a definition of community resilience, really, because we're talking about not just impact, but recovery from. So this would be more of a definition of community resilience. Okay? Which would be a function of vulnerability and then recoverability. So the several of these characteristics that I'm talking about here with respect to social vulnerability are adapted from Cutter. I am not pretending to have made these up. I'm not pretending to study these in detail, okay? But they have been published. They're widely used in the social science literature that is dealing with disruptive events and the impacts of those events on communities. Okay, so these aren't my words. These are adapted words from this research group in South Carolina. Okay, so a few characteristics of social vulnerability. One is socioeconomic status, which is a function of income and wealth and so on. Okay, so wealth enables communities to absorb and recover from losses more quickly, right? Wealth may imply insurance. Insurance may imply an ability to recover from some sort of disruption, whether we're talking about, a home being repaired after a disruption, or someone who has insurance, health insurance, who might be able to recover from a disruption because of their ability to pay for medical care, whatever it might be, the wealth that might enable someone to call tree trimmers to remove downed limbs from power lines, whatever that might be, right? Wealth enables a certain amount of a reduction in vulnerability. Therefore, low income or low status, socioeconomic status, might increase vulnerability. So that's why we're seeing a plus here. Low income or status would increase social vulnerability. Gender. This is a difficult one, but perhaps traditionally, it might make sense that women are, certainly they have lower wages than men, so they might have less of an ability to reach certain socioeconomic status to be able to respond to disruptive events. Also, historically speaking, they would have family care responsibilities that might make things difficult for being able to respond to a disruption. In any case, Cutter's group found that being female increased social vulnerability. And I don't mean here to put some sort of binary response on gender, but this is her research outcome used two genders, so I'm going to stick with that. Race and ethnicity. So there could be some language barriers that exist due to certain ethnicities that might make it difficult to respond, might make it difficult to follow instructions and so on, receive risk communications. Certainly there are fewer resources devoted by municipalities and governments to certain areas where certain races might live. And that's a function of poor governance, but that reality exists nevertheless. And Cutter et al. Found that being non-white increased social vulnerability. Age, being especially old or especially young, increases social vulnerability. Being within a community where there's high commercial or industrial development, increased social vulnerability. Might be a poor indicator, or pardon me, it might be an indicator of poor economic health, being in an industrial area, residing in an industrial area. Employment losses. Disasters exacerbate the number of unemployed workers in a community, thus resulting in slow recovery from a disaster. Being especially rural, that is far away from resources to cope with the disruption, or being especially urban, where there might be, for example, fewer ways to evacuate out of harm's way for certain types of disruptive events. Either one extreme or the other has an increase on vulnerability. Certain kinds of residential property might increase social vulnerability, particularly living in a mobile home. There are certain types of disasters that really impact mobile home living more than others. For example, here in Oklahoma with tornadoes, those can be especially harmful. Being in areas where that are highly dependent on physical infrastructure networks could increase social vulnerability, right? Being highly dependent upon, for example, a public transportation network, like in New York City, that tremendous reliance on that network might increase social vulnerability. Renters, so rental reliance on renting increases vulnerability. Could be an indicator of transient status, that is maybe less of a connection to a community. Perhaps less financial resources, which goes back to socioeconomic status, may reduce the possibility for shelter options, depending on rental status. Occupation, certain occupations might be more able to withstand a disruption. Professional, managerial would decrease, those kind of professions might decrease social vulnerability. Service sector might be more vulnerable to disruptions. Large families, higher vulnerability. Single parent households were found to have higher vulnerability. Education, less educational attainment increases social vulnerability. Of course, that's a socioeconomic idea. Also, perhaps lower educational attainment might lead to less of an understanding of warnings and risk, not able to accept risk communication as well for certain kinds of disruptions. Population growth, if there's a rapid population growth, that might mean that for a particular area, that might mean that resources and risk mitigation might not have kept up with that rapid growth. Arterial roadways may not have kept up with that growth. Access to medical services decreases social vulnerability. Those who are more dependent on social services would be more socially vulnerable. Those with special needs would be more socially vulnerable, and so on. So based on some of these characteristics, a social vulnerability index was developed by Cutter, and there are several others. We'll see some of those at the end, or we'll see points to the literature for some of those at the end. But Cutter's group put together a social vulnerability index that combines several of these indicators together. So she originally had 42 variables, applied principal components analysis to, you've probably talked about principal components analysis elsewhere in the curriculum. Broadly speaking, it tries to reduce the dimensionality of a data set to explain as much variability as possible with fewer variables. And here, the 42 variables were reduced down to the 11 most important, explaining roughly 3/4 of the variability in the data. And so those ended up being personal wealth, which is just an indicator variable earning less than 75,000 as a contributor to social vulnerability. Age, especially old, especially young. Density of the built environment where the community is located. Single sector economic dependence. So singular reliance on a particular economic sector, like, for example, in Oklahoma, oil development, for income generation creates vulnerability. Housing stock and tenancy, those that, depending on what kind of stock there is, mobile homes, for example, the higher the number of renters, the more socially vulnerable that community might be. And then here are several that deal with race and ethnicity, African American, Asian, and Hispanic. Those two races and that ethnicity increase social vulnerability. Again, this is from Cutter et al. And then Native American also increases social vulnerability. Occupation and infrastructure dependence. And so all 11 of these variables, or proxies for them, right? So these might be more qualitative kinds of variables, and proxies for them can be found from essentially the US Census Bureau and some other related sites associated with census data and ArcGIS geographic information systems. And so, broadly speaking, the way the social vulnerability index is calculated is you convert those factors into a percentage of the geographic area chosen. So we'll see a picture of this in a second, but for example, you would calculate a social vulnerability index at the county level. So what's the social vulnerability of a particular county, or maybe a zip code, something like that. And so how is this thing calculated? First, for this particular geographic area of interest, you convert all the factors into a percentage of the geographical area chosen. So for example, the percent elderly, the percent of the community that makes less than $75,000, and so on. You standardize those, normalize, okay, with z-scores, right? So this would be from basic statistics. You calculate a z-score. You perform principal components analysis on those z-scores, and then you sum them up with equal weights. Okay, so all of those are given equal weights, which could be problematic, right? Some of these factors might be more important to a decision maker than others. However, in the social vulnerability index, they're given all equal weights across those 11 factor groups. And so you get a picture that looks like this. So here you've got, this is from 2014's most recent county level calculation that you can easily find on Cutter's website. And you see certain areas are have high social vulnerability, medium and low. And so that could be from a variety of things. Yeah, just depending on the area, there could be different reasons why some of those different factors, some of those different 11 factors result in high, medium, and low social vulnerability. Okay, so why does this matter to us? So let's think back to that Shelby County, Tennessee example that you've seen before. Okay, and you remember we had interdependent water, gas, and power networks. And here's what that set of interdependent networks looks like in Shelby County, Tennessee. And remember, in Shelby County, this is where Memphis is located. This is in far western Tennessee, near the New Madrid Fault Zone, which is one of the areas in the country that could be considered for the next big earthquake. So that's why this particular case study is popular among those who study infrastructure resilience, in particular community resilience. And so recall this figure that we just talked about earlier. And so we're interested here in particularly recoverability, right? So how could we optimally restore after a disruptive event, okay? And so there was a particular measure that I worked on with some other folks where we measured resilience as a function of recovery over loss. Okay, so there's some amount of loss at time t, calculated here as the drop in performance, so that's vulnerability. And then to what extent is restoration taking place? Okay, so that's recovery at a particular point in time, right? So a measure of resilience could be, and this is just one approach, the extent of recovery at time t divided by the amount of loss occurring as the initial drop in performance. And so a previous student, and we'll see his paper here in a second, the title of his paper and all the information about that. Previous student looked into an optimization formulation for restoration of interdependent networks. Also, Andres Gonzalez has done some work in this, and he's probably presenting that in one of his lectures. And so we've got a bi-objective problem here. One is maximizing that measure of resilience that we saw on the previous slide. Here's another way of looking at it, where we're summing across time. We're summing across the nodes that have been impacted. We're summing across the networks, and we're weighting those networks. So this could be, set K could describe power, water, and gas networks, for example, right? And there could be some level of importance applied to each one of those, depending on the perspective of the decision maker. But this is essentially that recovery over loss function. And we want to maximize that value while minimizing cost. So what makes up the cost here? Well, there's some fixed costs associated with restoring nodes and links in the network. There's some costs associated with flow. This would be a traditional flow minimization, or pardon me, cost, max flow, min cost formulation in network optimization. And then costs associated with not being able to meet demand at different demand nodes. So if power is out, there's a cost associated with power being out here. Okay, so we got to fix this stuff. There's a traditional flow cost, and then there's a cost associated with not being able to meet the demand in those different networks. And we want to minimize that. So we want to maximize resilience, minimize costs, and those are competing with each other. Okay, maximizing resilience comes at a cost here. So this max and this min compete with each other. We have a few constraints in this optimization problem. I'm not going to go into detail on these. You can check out the paper if you'd like, but these are some traditional network flow optimization constraints. Here is constraints describing the interdependency of different networks. Here are constraints on the assignment and scheduling of different work crews. Okay, so how are we going to assign them and schedule them to repair? Here's a couple more. Here are some, these describe the improvement in flow depending on the extent to which a disruption is being restored, essentially. So if we're scheduling for different nodes or different links at different points in time, that means there's some improvement to the disrupted capacity going on in those nodes and links. And then finally, some constraints describing the nature of the decision variables. Are they non-negative? Are they binary? And so on. And so what do we get here from a small example that's contrived? So that we use a network generator to generate interdependent networks that have power and water characteristics. So the power network is in blue, the water network is in red, and then the interdependencies between those two are with green, and we see that graph here. Okay, again, a contrived example. And so what do we see here? I mean, there's not really a whole lot to say about this other than we applied our optimization problem to the interdependent power and water networks in that contrived example. And this is what we see with respect to restoration, the recoverability over time, if we assign 1, 2, or 3 work crews to each of these networks. Okay, so certainly restoration occurs sooner the more work crews you assign, but that comes at a cost. Now you can see some more analysis in the paper if you want, but this is just a general, what's an outcome of this optimization problem. We get this trajectory of the resilience measure over time for each one of the networks. But let's say we want to also account for social vulnerability. Let's say we want to make decisions about restoring these interdependent networks with social vulnerability in mind. Okay, we're not just repairing an electric power network just for the sake of, making the electric power network happy. There are people who rely on that network, and certain areas might be more socially vulnerable, might be less able to withstand and adapt to that disruption. So we want to account for that in our optimization problem. Okay, so we include in here measures of social vulnerability in the resilience measure. So this is a version of that resilience measure, that's recovery over loss. Okay, and in the cost here, we're accounting for not meeting demand. Okay, so this was the demand loss calculation, where we're accounting for social vulnerability, and also I should mention here, this is a population index, this P, that I'll show you here. So this V here represents social vulnerability, and that's a function of the social vulnerability index. We wanted to make that social vulnerability stand out in an exponential way. So we do an exponential function on there. And then this is population density. So we're accounting for social vulnerability and then also the density of the population in a particular area where demand is being met or not. And so here's, so we're not using a contrived example because we actually had to have social vulnerability values. So we're using Shelby County here. And these black dots here are the demand nodes for the Shelby County network. And we used a Voronoi diagram to essentially break up Shelby County by those nodes. So we're essentially associating that node with this area here, this node with this area, and using a Voronoi algorithm, you can check into that, what that entails. But essentially what we wanted to do is be able to say, for this particular demand node, what is the social vulnerability associated with that demand node? So we use the Voronoi approach, calculated social vulnerability for all these different locations. And so we could calculate social vulnerability down to the block level. That's not like city block, but there's a characteristic in GIS called block. And so that's where you see these different colors. So we have different social vulnerabilities in different blocks, and then essentially took the average of that social vulnerability weighted by area and assigned that demand node a social vulnerability index, essentially, in 4 categories. Okay, so we turned this picture into this, essentially. Okay, so these are the demand nodes in the electric power, gas, and water networks, and social vulnerability indices in 4 different buckets, essentially, 4 different percentile areas for each one of those demand nodes. Okay, so we've got social vulnerability for each one of the demand nodes in this Shelby County network. And so we can apply our optimization problem here. And we can try to weight the different characteristics in that optimization problem with the social vulnerability index and the population density index. And I mean, the result here isn't all that thrilling, but what do we see? We see if you don't use the social vulnerability index, you get a different result than if you do, okay? And that different result could really matter. We could really be assisting particular communities if we account for the social vulnerability index. And we see that there is indeed a different result. We get different trajectories of restoration depending on whether we try to address the needs of social vulnerable communities relative to not, okay? Yeah, so that's what we see with the implementation of the social vulnerability index. So if you want more details here, this is just a little bit of an introduction to this idea. If you want more details, the original paper that I showed on the restoration model, that appeared in Reliability Engineering System Safety back in 2019. And you'll see here that one of the co-authors is one of the speakers in this course, Laura Albert. We've got then the implementation of the social vulnerability index for the restoration model. And you see Andres Gonzalez, the other instructor for this course, involved in that. So that was the initial idea that we published in the International Journal of Disaster Risk Reduction back in 2019. And then a follow-on paper where we used the social vulnerability index to try to pick out the most important components in an infrastructure network. One area in reliability engineering that's been popular for decades is the idea of component importance. That is, how do you pick out the most important components in a system? What What's the most important machine on a factory floor, for example? There are different approaches, different philosophies on how to pick out what the most important components are. And we did this for interdependent networks with a social vulnerability and an equity perspective. And that appeared in Sustainable Cities and Society back in 2020. And again, you'll notice Chris Zobel, who's another lecturer in this course. And if you're interested in some other social vulnerability scores, there are others. Again, the Cutter approach is quite popular, but it's not the only one. The Department of Homeland Security has one itself. So those might be important to check out just in case you want to read a little bit more about this idea of social vulnerability. And that's it for this lecture.